There is approximately 33 million cubic kilometres of ice on Earth, with much of it contained in the huge ice sheets of Greenland and Antarctica. As global temperatures rise, that ice is melting. It is estimated that the Earth is losing around 1 trillion tonnes of ice per year. But how do we know this? It's all thanks to our eyes in the skies, satellite missions. In this video, we will explain how satellites are able to monitor the Earth's ice from space using remote sensing technology called altimetry.
So before we had satellites looking at polar regions, we really didn't know very much about them at all, apart from what people collected when they visited, and they're so huge, we can't possibly hope to measure all of them on foot. When satellites came around, we could see that they were really useful for looking at other parts of our planet, and eventually we persuaded the space agencies to launch missions over the poles. And now we have a really clear picture of what's happening there. A very different picture to what people thought before we had those measurements.
It's vital for scientists to have a strong grasp of how much ice there is on Earth and how much is melting for a variety of reasons. The ice sheets hold vast amounts of water which goes into the ocean when it melts, contributing to global sea level rise. Ice sheet mass balance is a key indicator of climate change, and monitoring changes in the Earth's ice helps scientists understand how the climate system is changing over time. Melting ice sheets can affect ocean circulation and global climate patterns. Accurate data on ice sheet mass balance improves climate models and projections so policymakers can prepare for future scenarios. But how does altimetry work, and what can it tell us about the Earth's environment and how it is changing?
So we have a sensor that's mounted on, it could be on an aircraft or on a satellite, which is a downward looking instrument, so it will fire a pulse of light, electromagnetic radiation, down towards the surface of the Earth, and that pulse will be reflected back from the Earth's surface and then received again by the satellite. And so, because we know the speed of light, we can convert that to the time it's taken for that pulse to travel to the Earth's surface and back again. And then we also know the altitude of the satellite, because we know the orbit really precisely, and we know the mean sea level. And so you can combine all that information to work out the height of the surface that the pulse is reflected back from.
As Tom mentions, there are two different types of altimetry technology used by CPOM scientists to estimate the height of ice sheets: radar and LiDAR. Although they both measure the same thing, they have different attributes. Radar signals can pass through clouds, but they also penetrate the ice sheet surface, and there has to be adjustments made to compensate for this effect. Laser signals, on the other hand, reflect from the actual surface, but cannot record when clouds are present. NASA's ICESat-2 satellite uses laser altimetry, while ESA's Cryosat-2 satellite uses radar. In 2020, the Cryo2Ice campaign, an ESA-NASA partnership, adjusted Cryosat's orbit to synchronise with ICESat-2, which has enabled near-simultaneous collection of radar and laser satellite data over the same areas.
The two missions are very important because they're giving us the proof that basically ice is melting around the world, and by using two different methods and techniques, but we are able even to combine them, and they say basically that the Earth cryosphere is changing, and this is happening because of global warming.
Recently in CPOM we did some work comparing different types of altimetry in Greenland, so radar altimetry and laser altimetry, from two different satellites. And one from Cryosat-2, which is a mission run by the European Space Agency, and ICESat-2 by NASA. And we found that these two altimeters agree really well over the same periods of time and same locations, and that's a really important finding. That means we can use them together to learn even more about the ice sheets. One of the benefits of altimetry is that it's higher spatial resolution compared to some of the other geodetic techniques that we use to monitor changes in ice mass, for example. So what it can tell us is about how individual glaciers are responding to climate change, and they all respond differently depending on how they interact with the Earth system. And so that's where altimetry is really important, particularly for the ice sheets.
In Greenland and in Antarctica, the two big ice sheets, and we also have land ice in the mountain glaciers all across the world. And when that ice is melting, it directly contributes to rising sea levels. So it's really important because around 40% of the global population live in coastal area.
So, we're interested in a lot of different properties of the ice sheet and how they behave, and so we can combine all these different observations. So altimeters tell us about changes in ice elevation and volume, but we want to know the mechanisms behind those changes, and so we would use other observations maybe to help us attribute to those changes. It could be changes in ice flow, or it could be changes in snowfall on top of the ice sheet, or an increase in surface melting. And altimetry can tell us something about all of those different behaviours.
Changes in ice sheet mass can be observed using altimeters, which measure the height of the ice sheet surface, but it also can be measured through gravimeters, like the GRACE satellite, which are able to weigh the ice from space through monitoring changes in the Earth's gravity caused by movement of melting ice as it enters the ocean. It's also possible to contrast satellite measurements of ice flow estimates with climate model estimates of how much snow is falling onto the ice sheet. The Ice Sheet Mass Balance Intercomparison Exercise, or IMBY, led by CPOM, is a community effort to bring together multiple estimates of ice sheet mass balance to gain the most robust assessment of how much ice is on Earth, how much is melting, and what this means for sea level rise.
We measure how much ice the Greenland and Antarctic ice sheets are losing, and what we can do when we aggregate lots of different satellite estimates of ice sheet mass balance, we can actually also try to reduce our uncertainties in our observations and then produce a robust data set that can be used, for instance, by the ice sheet modeling community, so that they can calibrate the ice sheet models and improve and reduce uncertainties in their projections of future sea level rise coming from the ice sheets. So within the ice sheet mass balance intercomparison exercise, we track ice losses from Greenland and Antarctica, and because we do that from satellite, so we can actually now have a monthly record of how the ice sheets are changing. So we don't really find a big surprise, because we have this now capability of monitoring month by month what the ice sheets are doing, which is very valuable, because then we can see whether the snowfall accumulation that we get in winter is enough to offset the meltings that we have in summer, for instance. And we found that Greenland and Antarctica have been losing mass more rapidly over the last decade.
It's important to gather data on the ground to complement the altimetry data we gain from satellite missions, but also to calibrate the information to improve accuracy, as well as to better understand the differences between radar and laser data.
So for instance, sometimes we have the chance of going actually to those places, and we have some campaigns. So we can have some airborne campaigns where we have similar instruments on aircraft that we use on the satellites to make sure that what we see on the ground is actually what we measure from satellites.
Climate science is huge. Everyone can't do everything, so we all have our specialities. But we found that climate models and satellite data go hand in hand with each other. And in fact, everything we've learned about climate change is thanks to those two things. We wouldn't know what we know today if we didn't have satellite measurements, and we wouldn't know about the future if we didn't have models. But the models need to be grounded in reality, and that's what the satellite observations provide.